Alright, so this is a retry of doing section 1 for NCCER Instrumentation 4, Module 4, Digital Logic Circuits. So, Module 4, Section 1. Just going to run through my highlights for this. In the trade terms, I've got the logic level is highlighted as an online test question. You need to have logic level, the voltages that represent logic 0 and logic 1 for a particular digital logic family. You know what those are. You need to read through the trade terms. A lot of the, like 5-volt logic is pretty common, but you need to know your different gates, like your AND gate, OR gate, NOR gate, XNOR gate, XOR gate, stuff like that. You know what a truth table is. We'll talk about propagation delay. You need to kind of know what this stuff is for this section. This first section of this chapter is probably the more important one. First sentence on page 1 is my first highlight in the text. Digital technology works by representing all information as numbers. I'm just going to run through highlights and stuff like that for the purpose of this video. 110, digital technology. First sentence of that is highlighted. Digital circuit components that are able to work together are grouped into collections. A collection of this kind is called a logic family. Moving on to page 2, we'll talk about power supply. Usually you'll have like your power supply will be related to whatever you're doing. Your stuff needs to talk to each other, so it needs to kind of be on the same type or level of power supply. Section 112. I don't have it highlighted, but you should know the first sentence. Digital technologies create numbers by using just two values, 0 and 1. The highlight, I do have the second to last sentence in that paragraph highlighted. The 1 value may be called logic 1, high, true, or on. All those are synonyms when we're talking about digital logic. The 1 value may be called logic 1, high, true, or on. Next paragraph, first sentence is highlighted. In order for digital devices to communicate with each other, they must recognize the same logic levels. So everything, 0 to 5 volts, everything in there needs to be reading 0 to 5 volts. Skip 2 sentences right after where you see logic window and italics, and I've got the next sentence highlighted. As an example, a popular 5-volt logic family defines an output voltage in the range of 0 to 0.5 volts as logic 0, and a voltage in the range of 4.5 to 5 volts as logic 1. Out to the side I wrote logic levels. These are logic levels. So looking up here on the board, you can see if your range is 0 to 0.5, it's going to give you a 0 every time. If it's 4.5 to 5, it's going to be a 0 every time. This is the undefined region, so it's neither 0 nor 1, but usually it's not going to change until it hits that next, so if it's logic 0, it's not going to turn on until it hits that 4.5 volts. Same thing. If it's logic 1, it's not going to turn off until it hits that 0.5 volts. Gates 113. First sentence of 113 is highlighted. The building block of all digital circuits, no matter how complex, is the gate. Don't have it highlighted, but the next paragraph, to know how a particular gate behaves, consult its truth table. So we can have truth tables like this. This is a truth table for a different gate. Going through the gates, 120 basic gates, moving on to 121. The AND gate. This is the first gate that we're going to talk about. 121, first sentence is highlighted. The AND gate is a device whose output is a logic 1 only if both of its inputs are also logic 1. So you need to know, for all of these different gates, you need to know the schematic symbols, kind of need to know how to read through the truth table, as well as an equivalent circuit. So this sideways mound looking thing is the AND gate, so I have to have A and B in order for my X to turn on. So my truth table, A and B are off, X is off. B is on, A is off, off. A is on, B is off, off. A is on, B is on, output is on. Only way to get X to turn on with an AND gate is to turn on both A and B. This is written in this circuit, so I got two normally open switches and a lamp. Both switches have to be closed for the lamp to turn on. I got it written up here. I got two normally open contacts. Both contacts have to be on in order for my motor to turn on. Moving on page 4, I have table 2 at the top as an AND table. That's your truth table for AND, which is what's on the board. This is an online test question, so they're going to give you this truth table or maybe a different truth table and say, is this for what type of gate is this for? If you look through there, you can see that the output is only on when A and B are both on, so you can see that this is an AND or a truth table for an AND function or an AND gate. Section 122, an OR gate. First sentence, not highlighted, but good to know. The OR gate is a device whose output is logic 1 if any of its inputs are logic 1. So, no highlights on this, but if I'm looking at my OR gate, this is my symbol for OR. You need to know symbols for these different gates. This would be a great opportunity to use the Quizlet flashcards or make your own flashcards for these different schematic symbols. You need to know these schematic symbols. So, equivalent circuit, you have two of these. They are in parallel. Either A or B turns on, my lamp is going to turn on. On my ladder diagram, I've got two normally open circuits or normally open contacts in parallel. Either one of them kicks on, my motor output's going to kick on. 1, 2, 3, the X OR gate. First three sentences are highlighted. A special form of the OR gate is an exclusive OR gate known as the X OR gate. It is a device whose output is logic 1 if just one of its inputs is logic 1. If both are logic 1 or both are 0, it will input a logic 0. So looking at the truth table for my X OR gate, this is directly the opposite. So you can see in my schematic symbol I have an OR gate, but I have a line in front of it. That line is going to give it its X. You want to key in on that line, gives it an X. So if I have neither one, it's not on. If I have one or the other, it's on. So from here, up to this point it acts just like an OR gate. But if I have both of them, it is going to be off. That is the difference between an XOR and an OR gate. Moving on to the NOT gate. 1, 2, 4, NOT gate. First sentence is highlighted. The simplest gate is the NOT gate, also known as the inverter. This is the symbol for a NOT gate, an inverter. So, an N, if you have N in front of something, or this is a NOT gate, but if you have N in front of something, that's going to give you this little bubble in the front, and it's going to change whatever you have coming into here for going into the output. So if I have 0 coming in here, 0, 0, 0, 0, 0, hits this, turns into a 1, outputs a 1. Truth table, put in a 0, outputs a 1. If I change this to 1, it's going to change, this inverter is going to change it to a 0. Last sentence, second to last sentence in that is highlighted. The symbols shown in figure 8 represent the NOT gate, and table 5 shows its truth table. You do need to know, like they'll talk about writing letters with a line over it. That just means that when it has a line written over it, that means it's not. It's the opposite. Modified gates. So this is moving on. Actually, I do have this symbol highlighted in the top right of page 5. You need to know what this symbol looks like. A little triangle with the circle is a NOT gate. Modified gates, 1, 3, 0. You got the N AND gate, not AND. So I have an AND symbol with my little bubble. Remember, this gives it its N. If I had a line right here, we give it an X. This bubble gives it the N. So this is an AND with a NOT. So this is going to act the opposite of an AND gate. I highlighted the whole first paragraph of 131. The N AND gate stands for not AND. and is simply an AND gate with an inverter attached to the output. The output will always behave in the opposite way to an AND gate with the same inputs. For example, if an AND gate has logic 1 on both its inputs, the output will be logic 1, but an AND gate will be output a logic 0 for that combination. So, same thing. 0, no inputs on either one, it's going to output a 1. Just B and not A, output 1. A, not B, output 1. If I have both of them, it's going to output a 0. It operates the direct opposite of an AND gate. NOR gate, so a not OR gate. Same thing. Not same thing. Schematic symbol. This is an OR symbol with a little bubble in the front. That means it's a not OR. This gives it the N. First paragraph, the last paragraph on page 5, the NOR gate stands for not OR and is simply an OR gate with an inverter attached to the output. Its output will always behave in the opposite way to an OR gate with the same inputs. For example, if an OR gate has a logic 1 on either or both of its inputs, its output will be logic 1, whereas a NOR gate will output a logic 0 for those combinations. So, same thing. Doesn't have A, doesn't have B, it's 1. If it has either 1 or both, it's going to be off. Behaves in the exact opposite manner as a OR gate. Going on to page 6, the XNOR gate. So, I have the OR. Start back. Alright, so 133, the XOR gates. XNOR gate. So this is an OR gate with an inverter with an X. So remember the line, PowerPoint back up. I've got an OR gate with an inverter and then the line. So this is an X. The X, remember the line gives you the X, the circle gives you the N, and then this is an OR gate. Online test question is the third sentence to the end of that paragraph, first paragraph in 133. For example, the XOR gate has a logic 1 on either, but not both of its inputs. Its output will be logic 1. On the other hand, an XNOR gate will be output a logic 0 for those combinations. So you just need to realize that whenever you're reading through your truth tables. And make sure you have that kind of memorized for the test. 140, combination logic. So adding this stuff together. So you can see, I've got an XNOR gate, an OR gate, and an AND gate combined together. You see my inputs are A, B, C, and D. My outputs are G, 1, 2, and 3. My highlight in 140 is the last sentence. Circuits made up of gates are known as combination logic. Analyzing combination logic. 141. On page 7, I've got the whole first paragraph highlighted. When you encounter circuits of this kind, the first thing you must do is analyze them to understand how they behave. The best way to do this is to create a truth table for the complete circuit. Remember that truth tables can become very large if there are a lot of inputs to the circuit. For example, the circuit shown in figure 13, which is up on the board, has 4 inputs. So its truth table contains 16 rows, which is table 9. 16 rows. This last sentence is what you want to key on. Every time you add an input, the number of rows in the truth table doubles. So if I added E, I would have 32 of these different rows because I'm doubling the number of combinations that I can have. Moving on to page 8, 143, issues involving combination logic. Third and fourth sentence has highlighted. There's always a delay between the moment an input change and the moment when the output reacts. This is called propagation delay. Kind of self-explanatory. 144, page 9. First 3 sentences are highlighted. One issue that may come up, particularly in industrial settings, is the need for digital output control. digital output to control something that requires a larger amount of current than the output can supply. In other situations, the connected device requires different voltage levels than the output provides. Both of these problems can be solved by using a special gate called a buffer gate. That is all my highlights for section 1. Section 2 through 4 will be in the part 2 video.